Good morning, good afternoon, and good evening, everyone. So today we're going to be continuing our linear algebra series, and we're just going to continue this idea of matrix multiplication, right? So just to briefly review what we've talked about in the previous video, basically we talked about what is the algebra of matrices. If we can do algebra with real numbers, then we can probably do algebra with matrices as well. And so we learned three concepts so far. One is addition of two matrices, in which we just add two, we just add two matrices with their corresponding entries, and we get a resulting matrix out of it. We also learned about scalar multiplication with a matrix. So we multiply a matrix by some scalar. And how that works is we multiply that scalar to each entry of the matrix, and we also get a matrix as a result. We also talked about this idea where if we have two equal matrices, that means they have the same dimensions or they have the same shape, and they also have the same entries. And lastly, we talked about, we had properties here, but we talked about matrix multiplication, which is this idea of multiplying a matrix by another matrix. And the trick behind it, since we already know how to multiply a matrix by a vector, we're basically multiplying a matrix by a column of vectors, right? Because we can think of a column of vectors as another matrix. Okay, so let's go to our next example here. So in this case, example 3. And the problem says, or the given matrices are as follows. So we let A be a 2 by 2. So this is 2, 1. That's just too big. 2, negative 1. Oh, no, it's just 1. 2, 1, negative 1, 3. And then we let B be another 2 by 2 matrix. So actually we call these square matrices since they have the same number of rows and columns. And we're being asked to find AB and BA if they exist. So actually we already know. So A, or in this case actually, A and B are both a 2 by 2. So both the product of AB and BA exist. So they both exist in this case, right? So let's actually solve for AB. So AB, well, we just multiply A by B. Okay. And we're going to get a 2 by 2 matrix. So this is 2 times 4, 8, plus 1 is 9. 1 times 4 is 4, minus 3 is 1. 2 times negative 2 is negative 4, minus 1 is negative 5. 1 times negative 2 is negative 2, plus 3. 3 minus 2 is 1. So I think that should be the answer. So it's 9, 1, negative 5, 1. Right? Okay, now let's try BA. So BA is actually, from the previous video, we know that the order in which we multiply the two matrices do matter because they produce different results. So what I'm saying here is that the product of AB is different from the product of BA. And I'm going to show you that right now. So 4 times 2 is 8, minus 2 is 6. So immediately we can see they're kind of different. No, they're not kind of different. They are different. Minus 2 plus 1 is negative 1. 4, -4, -6, -10, -1, negative, no, 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 no. 1 plus 3, 4. Okay. So immediately, we can see that the product of BA is different from AB, right? I hope that makes sense. Now, in some applications, we only need a single entry of the matrix product AB. Okay, so let's try this. So we let A be a matrix n by k. And we let B be k by m. Then we know some resulting matrix C equals AB is defined, or it works. Why? Because the number of columns of A is equal to the number of columns of B. K is K, right? K rows of A is equal to K columns of B. So we know that this thing works. So we say C is defined with jth column, or some column J. Okay, so let's try. So Cj is equal to ABJ. Oh, that's right. Which is equal to B1, B1J, A1 vector, B2J, A2 vector, all the way to BKJ, A vector. So that's one entry of the matrix C, right? Because we're multiplying A to B in this case. Okay, I hope that makes sense. Here we say where J is equal to 1. So these are iterations, right? All the way to n. Okay. Let me see if I can read this right. So B1, okay, for example, B1J is an element or an entry in B, right? And we're multiplying that by this vector. Oh, apparently that works. Okay, cool. Yeah, that does work. Okay, selecting the ith gives component from each of the vectors a sub 1 to a sub k. The formula for individual entries of C. What am I talking about? When we select some ith component from each of the vectors A, so let's say A sub 1 to K, formula for individual entries of C. So how's that gonna look like? So when we say Cij, this is only Cj. When we do Cij, that's the same thing as A sub I 1, right? B1j, oops. And then we add that to A sub I2, B2j, then we keep going here all the way to A sub ik, bkj. So note that we are multiplying each term from row I of A times the corresponding term in column J of B. So what we've been doing so far. And then we're adding the resulting products. And we actually call this the dot product, right? Now I'm not going to show a complicated picture of that, but let's do an example. Apply this idea. Let's do a dot product. But even if we don't know this formula, we already have an intuition of dot product from calculus 3, assuming we did take calculus 3. And I also have a video about dot products there, so you guys can feel free to check that one out. Okay, let's try this. Let's compute entries of C, which is a product of matrix A and B. Okay, so let's try. Okay, let's say A is, what is A? A 3 by 2. Say these are the entries of A. And these are the entries of B. So in this case, this works. This is defined since the columns of A are equal to the rows of B. So we know this works. Oh, this is negative. Okay, let's see. So let's actually start with C11. And so the way to compute this is we need row 1 of A and column 1 of B. So we need A11, B11 plus A12, B21, right? And then we keep going. Or actually, in this case, we're done. Since we only have 2 columns of A and 2 rows of B. And so this is the same thing as 2 times 2 plus negative 3 times 4. And so that's negative 8. And so that's how we compute it, right? And same idea. So just doing all of that. So here we have negative 8. At the bottom, we have minus 4. And then we just keep doing it. So I'm just going to fill all of these up. And feel free to check if these are correct. Okay. I think this is, yeah, 13 and then 10. Yeah, so that's what C is going to be. Let me do this. Okay. So that's the product of AB, which we get a resulting matrix C, which has those entries. Right. Let's talk about the identity matrix. And what in the world is that? So the identity matrix, so let's say A is n by n. Actually, I should have written it like this. A has a column of vectors A sub 1 to, oh, to M, my bad. And it's an n by m. We know that a plus 0 n by m is the same thing as a by additive identity, right? So that's the buzzword, additive identity. Oh, okay, so many stuff appearing in my screen. Additive identity. So what does that mean? We say that the matrix 0 and m is called additive identity. Because when we add something to this matrix, it's just itself without the zero matrix, right? And it is less apparent which matrix plays the role of the multiplicative identity. So here we also have a matrix I. Let's say we also have a way to multiply. I'm writing this in my own words. Matrix A by I to get A itself. And we call this the, right? When we're multiplying, one of the arithmetic laws, we call it the multiplicative identity. Because what we multiply to this A is just going to result to itself. So what am I saying? I'm saying A is multiplied by some I matrix. We're still going to get A. Now, what is this matrix I? This is the identity matrix. Right? So let's deduce what I is. So I, let's say, sub M, and it has these vectors. So we say the first columns of I, or A in this case, should be the same as AI, not ChatGPT. Of A and AI must be the same. So when we get our first vector A1, this is the same thing as, so the matrix A, I1, and I keep adding. So I11, A1, I21, A2. 2. And I keep going all the way to I M1 AM. So, okay. So the only way for this to hold is if, let's say, I1 is 1, and then we have zeros here. I2, 0, 1, 0. Then we keep going all the way to the end, right? So it's kind of like we're moving the ones wherever this ith position is. Okay. And there's actually a nice way to define this in linear algebra when we define our standard basis vectors. So let's note that actually I sub 1 is the same thing as E sub 1, right? And then we say I sub 2 is the same thing as E sub 2. We keep going, I sub M is the same thing as E sub M. So we say that how we define this I sub M is just the columns of E sub 1 to E sub M, which is just this guy over here. And we have a 0, 1, 0, 0, 1, 1. Okay? Okay, then I'll need to add that part. Cool. So that's the identity matrix. Right. That was a hell of a proof, but you should be fine. Okay, now let's talk about properties of matrix algebra. So as we have already seen, addition and scalar multiplication of matrices share many of the same properties as addition and multiplication of real numbers. However, not all properties of multiplication of real numbers carry over to multiplication of matrices, right? So for instance, we've seen that AB is not equal to BA. So let's actually look at matrix algebra. What are some of the properties that we need to be aware of? So we're doing a theorem here. So again, we let S be scalar. There we to write this nicely. Okay, let me just write it. I'll write it in a very mathematical way. 1, because it's shorter. 2, I'm lazy. And then we also let A, B, C be matrices. Doesn't say what matrices there are, but okay. Let's just say they're n by m. Really doesn't matter. I'll put a period here. Then each of the following holds in the cases where the indicated operations are defined. So For instance, let's say A multiplied by BC is actually the same as AB multiplied by C. Okay, those two are the same. Another property is A times the sum of two matrices BC is the same as multiplying the matrix A first to both B and C and then multiplying it. So that's distributive property. Then we also have A plus B multiplied by C, same thing as AC plus BC. So another idea of distributive property. And same thing for scalars. So we say S, and then we multiply it by two matrices. It's the same thing as multiplying some matrix first by S, the scalar, and then multiplying it to another matrix B. It's the same thing as this. We multiply B by the scalar and then multiply by A. So all of these three things are the same no matter what. And then we talked about, actually I'll put this in one column. AI is IA. So this is one of those cases where when we reverse the order of multiplication of matrices, it's still the same thing because I is an identity matrix, right? So, oh, that's it. Cool. Okay, there's a proof for each. We can do a proof for each, but I'm not gonna do that as this isn't a proof-based class. I'm gonna try doing more examples in this case. But yeah, hopefully everything makes sense so far. There's nothing too weird going on. We're just vibing. Okay, let's check this one. Right, moving on to example 5. Okay, have I? Oh, more stuff. Should be fine.